नायडू सर, हेलो।
अरे ज्वाइन कर रहा हूँ तुम लोग जल्दी से।
हाँ सर, शैल वी स्टार्ट?
हाँ या वी विल स्टार्ट।
ओके।
सर यार।
हाँ सर इज देयर।
हाँ गुड आफ्टरनून सर।
Good
हेलो,
afternoon. Good
डॉक्टर
afternoon,
हरि
sir.
कुमार नायडू। हेलो,
Good afternoon, sir. I am there.
गुड आफ्टरनून।
Good afternoon.
Thank you very much.
Okay.
Thank you very much for delivering this lecture.
Okay.
Okay, so we will start. He will introduce you, sir, and then we will start, sir. Okay, thank you. Thank you.
Yeah, I am muting myself.
Yeah.
Shall we start, sir?
Okay, you start.
Good afternoon, respected Dr. K. Shanti Swarup, Professor, Indian Institute of Technology, Madras, respected Head of the Department, Dr. Prema Dayagavani, respected Senior Professor Hari Kumar Naidu, faculties of the department, the students of 6th semester A and B, Electrical Engineering Department. I welcome you for this expert lecture on economical operation of power system by Dr. Shanti Swarup, IIT Madras. It's a pride privilege to have with us such a guest of eminent personality of high stature to guide us on this occasion. Let me tell you, sir, the GHRCE College of Engineering is the autonomous college, and electric department is accredited by the NBA. We are organizing the series of guest lectures of various eminent personalities from the academia and industries for every semester. For the sixth semester electrical student, for the subject power system dynamics, this particular lecture is being arranged. I am extremely thankful to Dr. Shanti Soru sir for accepting our invitation for on this occasion. Sir has completed his PhD in 1991 from Indian Institute of Science, Bangalore. He has taught many courses like electrical engineering, computer methods in power system. Sir has introduced new courses, power system optimization, smart powers, power system operation planning. He has been to the industry in the companies like Mitsubishi Electric Corporation, Milco, Amasgatsuki, Hogyo, Japan, from 1992 to 1996. He is having the industrial academic experience in Kitami Institute of Technology, Hokkaido, Japan, from 1996 to 1999, and IIT Madras since 2000 onwards. His area of research and expertise includes the power system, computer applications, operation and control optimization techniques, deregulation and restructuring power system automation and digital numerical protection, and web-based SCADA, computational intelligence and soft computing and applications, energy management systems, network automation, distributed artificial intelligence and multi-agents distributed computing, smart grid control, demand resource restoration, smart microenergy grids, information and communication technology, ICT for power system. He has 134 reported journals papers to his credit. So it is a extreme luck and the privilege to have with sir. Now I request sir to start his lecture. Sir, kindly.
Good afternoon, everyone. And thank you, Professor Naidu, for inviting me. Okay.
You can share, sir.
I'll be sharing my slides briefly, and please let me know if you can see this.
Do you have the share option you are having?
No, I am not finding the share option.
Okay, sir. One. Okay. And now you have been making a presenter. You can just share.
Yeah. I'll switch off my video after some time so that people can see me. Okay. Can you see the slides now?
You can see the slide.
Okay.
You can zoom it. I mean, you can make it full screen.
Yes, this is full screen only.
Okay, okay,
I'm saying if you can make it full
okay,
screen.
okay.
This is full screen. Okay, good afternoon, everyone. And Professor Naidu, thank you for inviting me here. I'm going to talk about power system operation briefly. And these are the contents of the presentation. Mostly about economic operation of power systems. And I'll introduce what is called as optimization techniques in power systems. Because economic operation is nothing but optimization. I'll be using these terms interchangeably. Most of my slides may start with the term optimization, but don't be alarmed because both of them are one and the same. I'll talk about economic dispatch, the formulation, the mathematics, and some examples, and various methods used in power system operation and optimization, like Lagrange method, lambda method, gradient method, reduced gradient method, Newton's method. The purpose of this talk is to make you aware how important this power system operation and optimization are. Usually this course is being offered in the pre-final and final years, and many students take this as an elective. Even in IIT, they take it as an elective because they want to do project in this area. And this course generally is taken to be, they take it as very easy, a scoring subject. But many students fail to realize that this course has much more to offer than just operation. So in this context, I'll introduce the topic of power system operation. We'll talk about what is normal operation, what is economic operation, why is the need to do economics, okay? And generally power system operation is nothing but generation load balance. That means the sum of the generation should be equal to sum of the load. This can be either done in a normal way or it can be done in an optimal way. We do an optimal way, it's called optimal generation load balance. This is also called as optimal economic operation. Okay. Sometimes it is called optimal dispatch. There are different terms: optimal dispatch, optimal load dispatch, optimal economic dispatch. These are the synonyms of the word economic operation. All of them are optimization problems. Optimization is the process of finding the best solution from a possible of several solutions. And this requires what is called a mathematical treatment of optimization problem. Okay. There are various variants of optimal problems. It's called economic dispatch, unit commitment, and optimal power flow. You might have studied this in your courses, but I want to add some delta information to the already knowledge you know, so that you can appreciate the course taught by your teachers. Okay. When you talk about optimal power system operation, is nothing but the balance of generation to load. The sum of the generation is called sum of the load. Okay, so what is non-optimal? Okay, a non-optimal solution is which is not optimal, and it can be basic solution or a feasible solution. But the optimal solution is always the best solution. Okay, there are three solutions: the basic solution, the feasible solution, and best solution. The basic solution is a solution which is not feasible. Okay. It a part of a solution but may not be feasible. It may violate some of the limits. Okay. A feasible solution is a solution which is basic but it is not optimal. Okay. So an optimal solution is one which is both feasible and optimal. With this three types of solutions we'll proceed ahead. One is called the basic solution. Feasible solution is also called a basic feasible solution. And the final one is called the optimal solution, which is called the best solution, which is both feasible and optimal. Now, let us start with these three solutions. Okay, as I mentioned, the aim is to find the optimal solution from the set of feasible solutions. This is what is called the process of optimization. This optimization is mostly limited to Department of Mathematics and Management Studies. Okay, our systems, have were the last to take the ideas from those people, and they realized that, by using optimization technique, there are several advantages. See, electrical power systems, as you're aware, they're more interested in operating the system more reliably. Okay, we should meet the generation. We should meet the load from the generation. First objective is to meet all the load. Okay, whether we make it optimal or not. Once you make sure that the load is met, then we try to optimize and make sure that the cost is minimum. Okay, that's why in power systems, reliability is more important and economy is next. But nowadays, economy and reliability are given equal importance. So that's why you need to study about economic operation of power systems. There are different types of power systems. Okay, let us look at it from a mathematics point of view. I'm sure all of you might have studied mathematics in your first and second year. Okay, I'll try to show this optimization problem like this. The solution of nonlinear or quadratic equations in power system is called economic operation, like economic dispatch, etc. The solution of nonlinear algebraic equations, okay, this is called as load flow studies. Okay, the solution of nonlinear algebraic differential equations is called stability studies. Most of the power system studies are complex dynamical systems. Okay, if you see, this economic operation is an optimization problem, whereas these two, load flow and stability, are not optimization problems. But if you add economic operation to load flow, this is what is called optimal load flow. It so happens that almost all problems in one form or the other can be formulated as an optimization problem. Optimization problem has become so widespread that almost all problems can be formulated. Let us see how. Take this slide which shows various methods. Time horizon from seconds to years. Okay. In seconds, automatic generation control is the first one which operates in seconds. This can be formulated as an optimization problem. Economic dispatch, which I'm going to discuss today, this can be formulated as an optimization problem. Optimal power flow optimization problem. Unit commitment optimization problem. Okay, from seconds to minutes to hours to days, every problem in power system can be formulated finally as an optimization problem. Even though we may not see this, we may only look at economic dispatch, optimal power flow, and unit commitment. But as when we proceed from months to years, okay, when we go from hours to years, from 4 to 8, then the optimization problem becomes more prominent. For example, unit commitment, okay, it's done usually for 24 hours or 1 week, 1 month, 1 year, so on. So you need to optimize. Okay, this is where optimization is felt. But unit commitment depends upon economic dispatch. That's why economic dispatch will study and see how it can be used in almost all optimization problems. Now, because I said mathematics plays a very important role, one of the first books, okay, on optimization and mathematics is called Power System Engineering and Mathematics by Eugene IIT. This was the first book which is there. And another new edition of this book has also come recently in 2016. Okay. Next, matrices and power systems, power system equivalence, applied mathematics. And this is one of the classic books. It's called Optimal Economic Operation of Power System. What I'm trying to say is mathematics plays a very important role in optimization. There are many books on mathematics and optimization, but these are the fundamental books. Okay, and these are the classic books. Okay, power generation, operation and control, power system analysis by Granger and Stevenson, and there's a new book called Optimization of Power System Operation. Okay, slowly we are going from power systems to optimization, and when we go further, there are several books on optimization. Okay, I've collected all of them to show how important this power system optimization has become. Optimization of power system operation, power system optimization in CAMS, artificial intelligence and power system optimization. Okay, optimization in power distribution, modern optimization techniques. There are many books which I've collected. Okay, and the recent book is this one, Convex Optimization in Power System. Okay, there's so many number of books in optimization. Okay, which I want to bring it to you that power system optimization is a very advanced field, requires a lot of expertise. Okay. Now, with this brief introduction, let us go into what is called as power system optimization, why it is important, okay, what you should know about this. Okay. Remember, in power system optimization problem, okay, there is various methods. First one is called as a conceptual problem formulation in terms of concepts. Next, you translate the concepts into mathematical formulation. First conceptual formulation, next mathematical formulation. Then the third one is the solution method. There are various methods widely used. These are called the traditional methods. Gradient method, reduced gradient method, Newton's method, linear programming, dynamic programming. Okay, the same thing I've shown here. Okay, these are some of the linear, nonlinear programming, interior point methods. Okay, and there are many methods used for different types of problem. Why do you need so many methods? Is there no simple method? Because the power system problem, being a very complex nature, you need different tools for different types of power system problem. Okay, for example, unit commitment requires dynamic programming. Economic dispatch can be solved using interior point method. Optimal power flow requires relaxation method. So all these different techniques. Now you can understand why you need different optimization problems for different power system problems. Now, let us see the power system applications of optimization. The three most widely applications are the economic dispatch called as ED, the unit commitment which is called as UC, optimal power flow called OP. Okay. These are the three widely used methods, and more than this you have what is called voltage reactive power dispatch, voltage reactive power V and Q dispatch. This can be further divided as active power dispatch and reactive power dispatch. Generator scheduling. Okay, this economic dispatch and economic dispatch and unit commitment together, it's called as generator scheduling, which is used for expansion planning. Expansion planning, suppose I want to plan for the next 10 years, 20 years. Okay, then I have to do generation expansion, transmission expansion, and distribution expansion. All of them require economic dispatch, unit commitment, and optimal power flow. This expansion planning, also called as network expansion planning, requires all these three. That's why you study economic dispatch. Okay, economic dispatch is the basic problem in all power system optimization. Let's see how do you formulate a typical power system optimization. I'll slowly introduce the mathematics here. Okay, usually we have three variables: f of x, g of x, and h of x. Where x is called the state variable. Okay, the objective function is f of x. The equality constraint is g of x. Inequality constraint is h of x. Okay. Objective function can be either minimized or maximized. Equality constraint, there will be very few, one or two at the most. But inequality constraints will be very large. In the power system problem, inequality constraints will be very large. Equality constraints, one or two. And objective functions can be one or many. This x is called the state variable. Usually, it is the voltage, magnitude, phase angle, P and Q, real power and reactive power. In most of the economic operation, we'll take only real power. Why? Look at this slide. Okay, this is a typical. You might have studied this various buses in power system studies. Okay, the slack bus, the PV bus, and PQ bus. Okay. If you see all of them, there are voltages, there is phase angle, there is P, and there is Q. All four are variables. If you see here, voltages, phase angle, P and Q. When it comes to economic operation, we take only P because P is called the working component. Because the cost is a function of P. Q is reactive component. It is not associated with any cost. It is only a local phenomenon. P is the one which is most cost effective. That's why we consider P. Okay. These four are the variables in load flow study. That's why we take four. Any optimization problem will involve all of them, but economic dispatch involves only P. So we'll consider only real power in our analysis. Now come to the mathematical formulation of optimization. This is how it is generally formulated. Minimize f of x subject to h of x less than 0 and g of x greater than 0. This is called the equality constraint, inequality constraint. They can be interchanged, okay? Where x is called the decision variable. This decision variable is also called as a control variable. Let us see in detail what is this x. The same formulation I have shown here, but the three important things are economic dispatch, OPF, and unit commitment. And the nature of power system problems are combinatorial, complex, multi-objective, Pareto-optimal functions, and mixed integer problems. Each power systems have different characteristics. Okay? Based on the type of power system optimization, various solution methods are. Okay? In fact, when it comes to large systems, Pareto multi-objective functions are widely used for obtaining a trade-off between different objectives. Now with this, let us see extended formulation. Remember I said we can write f of xup. Instead of x, I can even extend it to xu and p. X is called the state variable, u is called the control variable, and p is called the specified variable. This is how generally it is defined. Okay? X can be voltage and phase angle. The U is called the decision variable, contains all four: real power, voltage magnitude, reactive power, and angle. And the specified variable contains the voltage magnitude P and Q. Okay, angle comes only in X and U. With this, we can formulate the power system optimization in terms of X, U, and P. In case of economic dispatch, only one is used, real power is used throughout. When it comes to load flow, optimal load flow, and other things, we use many variables. That means the problem size becomes very large as we proceed further. This is how it is formulated. Okay, the same thing I have shown. What I wanted to show here is the objective function is nonlinear, the equality constraint is nonlinear, the inequality constraint is nonlinear. So everything is nonlinear. That's why the problem becomes very difficult to solve. We have to use iterative methods, nonlinear programming methods. In some case, we have to use heuristic methods. Okay. And this is an overview of what the three methods. Okay. In economic dispatch, only real power is used. In unit commitment, only real power is used. Here, this is a minimum cost of operation. Unit commitment, minimum cost of operation over time. Okay. We'll discuss what is this. And in optimal power flow, we have both real power and reactive power as variable. We minimize the cost, we minimize the loss, we minimize the voltage deviation. We have three objectives, either which can handle individually or combined. You can see the various methods in all of these things. What you observe here is there is gradient method and Newton method, which is occurring for economic dispatch and optimal power. But unit commitment methods are different. We have priority list and dynamic program. Within the economic dispatch and unit commitment are same. Once you have cost over time, these methods no longer hold good. Okay, you have what is called priority list and dynamic programming, and branch and bound methods, various methods. That means there's nothing like one method which you can use throughout all optimization problems. Same thing. There are various methods for linear programming, nonlinear programming, interior point methods. These are the various methods widely used. Okay. Why I'm showing this is interior point methods, okay, are gaining more importance. This is also called as the Karmarkar's algorithm, which is gaining more importance for large-scale linear optimization problems. That means we transform a nonlinear objective function to linear objective function and so on. The advantage of this is you can obtain the solution in a few iterations. That is the advantage of interior point. And these are some of the variables, okay? Different types of control variables, objective functions, the constraints and solution methods. Before we go into economic dispatch, we want to show when you want to minimize the cost, the variables either can be P generation or Q generation, but we take only P generation most of the time. When you try to minimize the transmission loss in a network, sometimes you have to take the phase shifter angle, okay, as one of the control variables. When you minimize the control shift, you have to take the tie line flows. Okay, there are various objective functions, various constraints. Okay, most of them are generation load balance, equality constraints, inequality constraints. If you see here, various methods are used. Linear programming is used, nonlinear programming, integer programming. The purpose is to show that various numerical optimization methods are used for different types of problems. There's nothing like you can say one method is suitable for all the problems. This is what makes power systems challenging. Okay. These are the various optimization methods, whatever I mentioned. Traditional methods and modern heuristics method. This is what we discuss: linear programming, interior point method, Newton's and gradient method. They're called direct analytical methods. These methods they construct a solution. Okay. For example, for unit commitment, branch and bound, dynamic programming, you construct a solution as you proceed. Okay. Modern heuristic methods are gaining more importance. Okay. Taboo search, which is deterministic. In probabilistic, you have simulated annealing. In population-based methods, you have particle swarm, evolutionary algorithms, genetic algorithms. These are gaining more importance nowadays because they can handle a problem far better without any mathematics. These are called population-based methods. With this brief introduction to optimization, let us go into economic dispatch. Economic dispatch is to minimize the fuel cost of generators. Okay? Either it can be economic dispatch or optimal power flow. Okay? Economic dispatch, including line and voltage constraints, is called optimal power flow. Okay? You can either have security constraint, economic dispatch, and operation. The main aim to determine the output of generators. Okay? Let us see economic dispatch without loss and with loss. This is a typical formulation of economic dispatch without transmission. The aim is to minimize the cost of generation. This is what is called the cost of generation. AI PGI square plus BI PGI plus CI. Okay. This is called the fuel cost of generator. Constant term, a linear term, and a quadratic term. The whole thing is quadratic. Number of generators. Subject to the equality constraints of power generation is called the power demand. Here power demand is fixed. The power generation keeps varying. And each unit should lie between the minimum and maximum. The same thing I can formulate like this. Objective function minimize f of t, sigma pi gi, subject to equality constraints and inequality constraints. This is a notation for each. If you see here only real power, reactive power, and the fuel cost of generator given by this. Here, there are various ways of representing this fuel cost. Either you can use it as AI PGI square plus BI PGI plus CI, or AI. There are different ways of representing the fuel cost characteristics. Either you can show like this, or you can show like this. Whatever it is, a quadratic term. Okay. In most industries, they neglect the constant term and they only show BI plus 2CI. That means they take the derivative of this. BI plus 2CI PI. They use only this for representing the generator cost. This is what is called incremental heat rate or piecewise. Let us see why this is important. Okay. A is a fixed value. Only B and C are important. That's why we take only B and C. B and C are more important in the generator cost. Let us see how. This is a typical generator fuel cost curve. Okay. If you plot this quadratic curve, it comes like this. Each has its own P minimum, P maximum. One is called the heat rate curve or fuel cost curve. Both are same, multiplied with some function. If you take the derivative of this, it becomes linear. Okay, if you take the derivative of this, it's Bi, beta I plus 2 gamma I Pi. So it becomes a linear. This is what is called incremental fuel cost curve. Okay, this is mostly widely used in the analysis. For example, generator fuel cost curve. This is called quadratic cost curve. Okay, this is called, if you approximate by small linears, it's called piecewise linear. This is called piecewise linear cost curve. Both are same. Instead of quadratic term, I make it linear segments connected together. We take the derivative of this. Because it's linear, it is a constant. This is called the piecewise constant incremental fuel cost curve. Instead of using a quadratic curve, most industries use either this or this. Okay? This is how the segments are used. This is how. Either you can have this, the fuel cost and incremental fuel cost. Okay, most of the industry uses only B plus 2C, B plus C. If the derivative of this, it will be a straight line. If it is piecewise linear, I get stepwise. This is widely used by industry. Okay, academic people use AI, BI, CI, but industry people use only BI and CI. At the end of this, we'll understand why industry uses B and C. They'll not take A into account. Take for example, some of the problems will be given like this. Okay, they'll give either the fuel cost curves at different values. Unit 1, 25 megawatts to 200 megawatts. These are the operating points. 25, 200. These are the points in between. Each unit has its point. Or the unit can given as incremental fuel cost. Okay, at different points, what are the values? Okay, industry uses either this or this to solve. This is very easy to solve because the purpose of showing this is where what is called a graphical solution. Okay, most of the economic dispatch problem can be solved by means of graphs and plots. As we proceed further, we shall see. Okay. Now let's come back to formulation. This is what is called a generic formulation. Okay, total generation is called a total load plus losses. Okay. Here, for time being, we'll ignore the losses. Total generation equal demand plus losses. Okay. Once you formulate, but this P loss is a function of PGI. Okay, that's what we'll see. When you consider an unconstrained minimization problem, okay, you have to make the gradient of this function to be 0, where f of x is the objective function. It's called grade f. Grade f should be equal to 0. Where x is a function of x1, x2, x3. This is what is called an unconstrained minimization problem. Here we use what is called as a Lagrange constraint, Lagrangian constraint. This is called minimization with equality constraint. We have an objective function f of x and equality constraint g of x. So we combine this with a multiplier is called a Lagrangian multiplier. Lambda is called the Lagrangian. F of x, objective function plus lambda times equality constraint is called the Lagrange. It is a function of x and lambda. Okay. The necessary condition for a minimum is the gradient of L of x should be equal to 0. The gradient of L of lambda should also be equal to 0. This is a mathematics because the two parameters x and variables are x and lambda. The x can be power generation, Pg1, Pg2, Pg3. Okay, this is how it is done. Okay, objective function plus lambda times equality constraint. You take the first derivative, equate it to 0, we'll get the necessary condition. That means the incremental fuel cost should be equal to lambda. This is the necessary condition for a minimum or optimal operation. The same equations we have written here. Okay. If you see here, this lambda can be calculated only from AI and BI. AI, BI are the fuel cost coefficients. Once you take the first derivative equal to 0, you can calculate PGI by this relation. Okay. Once you substitute here, you can get lambda in terms of PD plus sigma of this one. If you see here, this is a function of AI, BI, and P demand. If you know the P demand and fuel cost coefficients, you can calculate the lambda. Okay, this is what is called the Lagrange multiplier method. And also we have what is called as B loss coefficients method. When you consider transmission losses, the power loss is given like this. Okay, GIJ, PGI, BIJ into VJ. What is this B? Okay, B is called the B loss or the conductance matrix. Okay? If you expand this, the P loss, if you expand, you can write into 3 terms. B00 plus BI0 plus this one. That means constant term, a linear term, and square term. Okay. Because this is more prominent, we usually neglect these 2 terms and consider only the 3rd term in most of them. This is called the George formula and Cron's formula. We'll try to see an example how B loss coefficients should be calculated. For a given network, B loss coefficients are fixed. These are calculated well in advance. Okay. Once you calculate this, this is an accurate method for calculating the transmission losses. Okay. This is an accurate method. There is also approximate method. Okay, where you consider only the 3rd term and use it. Now, once you consider economic dispatch with loss, this is how it is. This is a transmission network. Okay, this is the fuel cost, this is the turbine, this is the output of the generator. We have transmission losses, this is the period. Objective function is minimize equality constraints. Minimize the objective function subject to the equality constraint. Sum of the power generation minus power demand minus P loss is equal to 0. Or sum of the power generation is equal to P demand plus P loss. All of them, all the power generation should be lie within the minimum and maximum limit. Okay. If you see here, with and without loss, if you compare, okay, objective function is the same, inequality constraint is the same. Only equality constraint, this is without loss, this is with loss. Okay, this is how. Okay, only the equality constraint changes when you consider losses. Inequality constraints and objective function remains the same. Just to illustrate this point, I have shown. Okay, same thing here. Okay, but this P loss, okay, is a function of power generation. It is not fixed. Here P demand is fixed. Here I showed it as PL, but PL is a function of PGI. Okay, P demand is fixed. So this function of P loss as a function of PGI or power generation makes the problem difficult to solve. Okay, that's why you need an iterative method. Okay. If you add, here we had only one inequality constraint. Okay. In practice, there can be many inequality constraints. These are called as security constraints. Okay. Minimize the objective function, equality constraint, power generation is equal to power demand plus power loss. In addition to the generator minimum maximum limits, you have the limits on the voltages and limits on the current flowing in the line. These are called as security constraints. Okay. Why I am showing this is what is called security constraint economic dispatch, SCED. Okay. If you consider voltage and line flows or power flow limit, this is called a security constraint economic dispatch. Everything remains the same. The number of inequality constraints keeps on increasing as we proceed. This is the B loss coefficient. Okay. We take only this term. You see here, we approximate only the final term, which is the square of power generation and into BIG. This is called the B loss coefficient. The first two terms we ignore and take only this term. When you do with losses, this is how the formulation is. Minimize the cost. Remember, some books write it as A alpha I plus beta I PA plus gamma I PA square. Some people write alpha I PA square plus beta I PA plus gamma. Irrespective of this, but still it's a quadratic function. Okay, this is how the formulation is. And once you do this Lagrangian multiplier, lambda times, okay, this is called Lagrangian objective function for lambda times the equality constraint. If you take the first derivative equal to 0, we get the following condition. That means partial derivative of cost with respect to Pi is equal to dCi by dP. That means the incremental fuel cost of all units should be the same. This is the condition. Incremental fuel cost of all units should be the same. When you have a penalty factor given by Li is equal to 1 by 1 minus dou Pi by dou Pi. This penalty factor is used to determine okay, how far the equality constraint is satisfied. Usually we assume a initial value of lambda and try to solve. We try to calculate the power mismatch and try to update the value of lambda k based on the incremental fuel cost. This is a typical procedure. We'll try to see this by means of an example. And we update the value of lambda. This lambda is called the penalty factor. And we try to adjust in such a way that lambda remains constant throughout the optimization. This is the purpose of lambda. Okay. This is lambda, this value of lambda. This is a power generation. For this incremental fuel cost curve, this incremental fuel cost curve, which should intersect all at the same point. For example, for optimal economic operation, all units should operate with the same incremental fuel cost curve. Unit 1 has 8.5, Unit 2 has 8.5, Unit 3 has 8.5. Okay. If all of them have the same incremental fuel cost curve, then you say that optimal economic operation has been reached. This is called what is called the Lagrangian multiplier method. Whatever I discussed here, this is without loss. Okay. The necessary conditions are given like this. The incremental fuel cost should be the same. Okay. If you see, this is called incremental fuel cost, and this is the most important parameter. Why is lambda the most important parameter? We shall see here. This is without loss. If you add loss, this term comes into picture. Then you take the partial derivative with respect to PGI, you get this relation. So you will get an incremental fuel cost curve. Okay. An incremental transmission loss. Once you have this formulation, I don't want to skip more into this one. Okay. This is what is called the Lagrangian multiplier method. This lambda is used for calculating, okay, the penalty factor or incremental transmission loss. If you see here, this is without transmission loss and with transmission loss, how the relation keeps changing. Okay? This is the difference between Lagrangian multiplier method. I don't want to go more in detail. The purpose of showing this here is the power generation of units, PGI, can be calculated using the B-loss coefficients. Once you know the B-loss coefficients, you can calculate the power generation of units. Advantage is you can calculate this in one step, okay? Deterministic. Instead of iterative method, knowing the B-loss coefficients and knowing the A and B, you can calculate the power generation of units. This is a Newton method, we'll discuss it later. Okay. Now, the conditions for economic operation is incremental fuel cost of all units should be the same. This is a condition for optimum. This is called inequality constraint. This is equality constraint without loss, equality constraint with loss. Okay, because this PI is repeating here, the solution becomes difficult to solve. Okay. These are the conditions for economic dispatch. Okay. If the power generation lies between minimum and maximum, this is equal to lambda. If incremental fuel cost is less than lambda, you have to fix at the maximum value. If it is greater than lambda, you should fix at the minimum value. These are the conditions. We shall see this for a typical problem. Okay. We'll see this Lagrangian functions. Okay, let us come with an example. Okay. Take a typical example. I just want to show whatever you have done. This I have taken from Woodenberg. I just want to show all the steps involved in solving. This is the fuel cost curve. Okay. This is given by this AI plus BI PI plus CI PI square. Okay. 3 units, unit 1, unit 2, unit 3. There are no losses. First, you take the first derivative of this and equate it to lambda. This is 7.92 plus 2 into this is equal to lambda. We have 3 equations. Take 3 derivatives, equate to lambda. Okay, and the sum of the power generation P1 plus P2 plus P3 is equal to 850. So how many variables are there? P1, P2, P3, and lambda. 4 variables and 4 equations. Okay, this can be solved, and once you solve this, you get lambda is equal to 9.148 and P1, P2, P3. Okay, this is the typical solution of economic dispatch without loss. Now, if I change one of the thing, unit 1, okay, instead of 1.1, I multiply by 0.9, okay, I'll get it as this one. Okay. I change the fuel cost of unit 1 while 2 and 3 remain the same. So what I do is, if I solve this, I'll get lambda as 8.424. Once I get lambda, I try to solve, I get P1 as 704, P2 111, P3. But each unit has minimum and maximum limit. Sorry, it is with limits, not without limit. P1 should lie between 150 and 600. P2 should lie between 100 and 400. P3 should lie between 50 and 200. The total generation should lie between 300 and 1200. You see here, P1 is 704 is greater than 600 megawatts. So I fix P1 at 600 megawatts. Okay. P3 should lie between 50 and 300. It is 32. It is less than the minimum generation. So I fix at the minimum generation. So I fix P1 at 600, fix P3 at 50. The remaining balance P2, I take it as 850 minus P1 plus P3. Okay, because I know P1, P3, I get P2 as 200. So this is how the new dispatch is 600, 200. This is called a feasible solution. Remember, earlier I said this is called a basic solution. It is a solution, but it's not feasible. Okay, this is a feasible solution. It is satisfying the limits, but it's not optimal. Understand? That's why I said basic solution, feasible solution, optimal solution. This is the basic solution. This is a feasible solution. But how do you know what is the optimal solution? This is where economic dispatch comes into picture. All three are solutions. This lies within the limit, but this is not the optimal solution. How do you know which is the optimal solution? This is where we use economic dispatch. Here, take for example lambda. Calculate lambda 2. Why do we calculate lambda 2? Because 2 lies between the limit, okay, 100 to 400. Okay? 2 is normal. Okay. Then I calculate lambda of this one. P comes as 6.826. P2 is within limits and lambda 2 is equal to this one. Then next I calculate for P1 and P2. Incremental fuel cost P1 at 600 is 8.016. Incremental fuel cost for P3 at 50 is 8.4. These are the things I have written as comments. P1 hits the maximum limit. So lambda 1 is 8.016. P3 hits the minimum limit. So L3 is 8.4. We have three values of lambda 1, lambda 2, lambda 3. How do you know which one is the best? This is where you require logic. Okay. L1 is the lowest. Next, L3 is the next highest, and L2 is the most high. This is very high. This is very low. When in economic operation, the incremental fuel cost should be very low. Okay. Look at it. This is the logic. Okay. Since the L1 of P1, okay, is small compared to L2 and L3, P1 is fixed at its maximum value. I fix P1 at 600. Then P2 and P3 are adjusted for a common lambda. I fix P1 at 600. Why? Because L1 is the lowest. Then I adjust unit 2 and unit 3. They'll have a common lambda. P1 is fixed and P2, P3 are variable. Then I'll solve these equations. How many unknowns? P2, P3 and lambda. Okay. This is one equation. This is one equation. And the third equation is equality constraints. P2 plus P3, P demand minus P1 plus P. So three variables, three equations. Once I solve, I get lambda as 8.576. And once you know this lambda, I recalculate P2 and P3 as 187.1 and 62. If you observe here is this lambda 8.576. Okay, it lies between, this is for 2 and 3. It lies between L2 and L3. 8.576 lies between this one. So this is the final thing. This is the equation. This is unit 1, which is fixed. I calculate lambda for this one. I get P2 and P3. This is the final values of P1, P2, and P3. Okay. L1 is fixed. P1 is fixed at 600 megawatts with incremental fuel cost. P2 and P3 have the same incremental fuel cost. The total generation is 850 megawatts. What the observation here is P1 is cheaper. Okay. How do you know P1 is cheaper? Because look at this A, B, C. This is called the C value. This C value is less than this and this. The C value of unit 1 is less than C value of unit 2 is less than C value of C1 is less than C2. Hence, P1 is cheaper. By looking only at C value, you can know which unit is cheaper and which unit is expensive. This is called the A, no load cost, incremental cost, and this is C, A, B, and C. This is how the economic dispatch is done. Okay. This is without loss, but with limits. So it should be without loss and with limits. Now let us do another example with loss but without generating limits. Take the same problem, 3-unit system. Okay, I've considered the loss function like this. Okay, this is using B loss coefficient. I took only the quadratic term. This is for unit 1, unit 2, unit 3, and the sum of the generation equal to 850 megawatts. The same equation. If you take the P loss like this, okay, I write the incremental fuel cost dF1 by dP1 is equal to lambda into 1 minus dou P loss by dou Pm. Okay. If I take the first derivative of this, 7.92 plus 2 into this P1 is equal to lambda into 1 minus dou P loss. Dou P loss by dou Pi is, okay, this is square. So 2 into 0.403 P1. So how many equations you have? This is for unit 1, unit 2, unit 3. Okay, and this is equality constraint. We have 4 equations and 4 unknowns. Okay, what are the 4 unknowns? P1, P2, P3, and lambda. But P loss is also a function of Pi. So how do you accommodate this? Because P loss is a function of Pi. Okay, so this is not fixed, this is variable. So how do we do is, initially we assume P loss to be 0. We assume P loss to be 0 and then calculate all these things. This is the procedure. Okay, that's all. How do you solve this? I have prepared a detailed procedure. We assume P loss to be 0, calculate P1, P2, P3, and solve. This is what is called the iterative method. We shall see this. Okay. This is with losses. Same thing I have shown here. This is the step procedure. Pick a starting value of P1, P2, P3. Calculate the incremental transmission loss. Calculate the lambda that makes P generation over P load plus P loss. Use lambda, calculate P1, P2, P3, and repeat step 2. This is the procedure with loss. Let us see each one. Step 1. Pick the initial starting values P1, P2, P3. Because the load is 850, assume losses to be 0. P1 is 400, P2 300, P3 150. Where sum them, it is 850 megawatts. Even the losses are not 0, assume losses to be 0. So it is not correct. Initially assume losses to be 0. Then I'll update the losses. I know the loss formula. I calculate the incremental transmission losses. Okay. Now I substitute this here. P loss in this, I get the losses. Even though I assume the losses to be 0, based on this P, I calculate the losses, 15.6. So the total generation is 850 plus 15.6, 865.6. Then, using this relation, I try to calculate the lambda that makes P generation is equal to P load plus P losses. Even though I assume loss to be 0, okay, I use this incremental cost relation. P generation, P1 plus P2 plus P3 minus P demand minus P loss is equal to 0. This is called the equality constraint. How many variables are here? 1, 2, 3, 4. P1, P2, P3. 4 unknowns, 4 equations. Okay? 4 unknowns, 4 equations. I try to solve. Once I solve this, I get a lambda value of 9.5252. And I get P1, P2, P3 as this value. Okay. Next, I repeat this procedure. Okay. I use the, now I use these updated values of P to calculate P loss, 15.78. Earlier it was, P loss was 15.6. Now with the correct values, I get 15.78. Then using this P loss, I try to calculate P1, P2. Again, I calculate lambda in P. Okay. This way I repeat. This is what is called lambda iteration method. I repeat the process like this till I get a combined solution. I assume P1 to be 400, P2 to be 300, and P3 is 150. I get losses as 15.6. And this is the lambda. And again, I correct the values of P1, P2, P3. Then calculate the value of lambda. Like that, I repeat. This is called an iterative method. Till lambda is constant, the losses are constant, and the power generations are constant. If you see here, I assumed initial P1, P2, P3 like this. Total power is 850, power demand is 850, losses. Even though, okay, losses supposed to be 0, I calculate based on this. Final value, P1, P2, P3. Okay. Losses are 15.83. Okay. This is the lambda. What you can see here is the lambda will be around the same value. Okay. P1, P2, P3 change based on the values. So this is economic dispatch with losses, and this is how the lambda keeps changing. So in this economic dispatch, we should know what is P1, P2, P3 losses and the value of lambda. Sometimes this initial value, here I assume the value of P1, P2, P3. In some other methods, I assume the value of lambda. Here I assume the values of P1, P2, P3 and calculated lambda. In some other approaches, I assume the value of lambda and calculate P1, P2, P3. This is called the lambda projection method. And here, suppose I want to know what is the cost. Okay. P1, P2, P3, loss is 0. This is the cost. Once you include loss, the operating cost will be more. Okay. This is okay. When you consider losses, the operating cost is more because we account for the losses in the network also. Okay. If you see here, P total is this, but 850 plus this one, okay, losses is 14.3. This is the P demand plus losses is equal to P generation. This is a typical economic dispatch example. This we've seen. What is lambda iteration method? Next we'll come to the graphical solution. Okay. Remember, operators in a control center who makes decisions, okay, who do real-time decision making, they use what is called a graph method. This is what is called graph and ruler method. This is called a ruler. This is called the graph. This is the widely used method by industry. It's called the graph and the ruler. This ruler, operators, they try to change up and down. The main aim is the incremental for fuel cost should be same for all units. You see here, this is striking here, but here, this is not intersecting this plot. It is something at the minimum. Okay? The sum of the power generation should be equal to sum of the individual power generation should be equal to the total power demand. This is the way. This is what is called graphical solution. This is what is called adjustment of lambda. This is called lambda. Adjustment of lambda to satisfy the equality constraint. Or in other words, this is the flow chart. This is the method. Remember I said conceptual formulation. This is what is called the conceptual formulation. Next, mathematical formulation. This is also called as lambda projection method because you try to project the value of lambda. Here you assume a set of lambda, calculate the power generations, calculate the error in equality constraints, P load minus sum of P generation. With the first iteration, repeat, check for the tolerance, error. If error is satisfied, stop. If not, repeat this loop. This repetition is called as projection. What is meant by projection? This is called as projection. This is what is called the lambda projection. What is the difference between this and this? This is lambda. Lambda should be the same. Corresponding to lambda, the sum of power generation is equal to power demand. Here, initially assume some value of lambda, lambda 1. X-axis is the lambda, y-axis is the error. Error in equality constraints. Power generation 1 plus Pg2 minus Pg3 minus power demand. This is error. Error can be positive or negative. First, I calculate lambda. Error is positive. I project the lambda here. This is the error. In the next iteration, I select in such a way that the error is negative. I will select lambda such that the error is negative. Okay, this comes here. The third iteration, I select such that error is positive. Each and every time, the error keeps decreasing. Error becomes 0. This is what is called the lambda projection method. Okay. The principle of operation is adjustment or projection of lambda to satisfy the equality constraint. So far, we are considering only satisfying the power generation is equal to power load constraint. Okay. In all Lagrangian method, other things, we consider only equality constraint satisfaction. Do not consider inequality constraints. Okay. Take, for example, lambda projection method. Okay, how to use? Here, if you have the fuel cost functions like this, A plus BP plus CP square plus DP cube, I've added a new term, cubic term. If I have quadratic, I can solve using Lagrange method. If I have a cubic term, which is very common use, okay, Lagrange method cannot be used. And use some other method. Okay? So lambda projection method can be used for solution of economic dispatch with higher order cost function. This is what is called higher order cost function. This is called a third order. Suppose I have 3 units, A, B, C, D values. Okay. And each unit has its minimum and maximum limit. Okay. Either the solution here is assume initial value of lambda, then calculate P1, P2, P3. Next, adjust the lambda such that this will converge. How you adjust it is trial and error. There's no guarantee for conversion. If you see here, the first iteration I assume lambda to be 8. I get P1, P2, P3 and total generation. The next, I increase the lambda by 0.8, 8.8. I get one error. Okay, but this should be, demand should be 2500. This is less than demand. I increase the value of lambda. When increase the value of lambda, this is power generation is greater than 2500. Then I decrease the lambda. Okay, 8.57. It is almost close. Okay, 2526. It should be 2500. I repeat trial and error in such a way that this is the final solution. P1, P2, P3 and P demand is 2500 and corresponding. But the challenge, how do you select the initial value of lambda? What happens if you select a different value of lambda? Suppose I start with lambda is equal to 10. Okay, it keeps changing. This, if you take lambda is equal to 8, it has converged in 5 iterations. If you take lambda is equal to 10, it has taken a lot of time till the 10th iteration. It has converged. If you see here, the final result is the same. Okay, but this has taken more iterations to solve this as less. So there's no rule saying that one method will work. Okay, fortunately, this has also converged in 10 iterations. Sometimes it's so. Suppose I take 15, this may not converge. Suppose I take 5, this may not converge. So how do you know what is the starting value of lambda? Even though this method is good, you should make an approximation for the initial value of lambda. Okay. Even the final results are same. If you see here, P1, P2, P3, P1, P2, P3 are the same. But how do you know what is the starting value of lambda? Is it any other way? Okay. This is where we have methods like gradient method, okay, and Newton's method coming into picture. Let us see what is gradient method. Is widely used method. It's not only used for economic dispatch, it's almost all power system optimization problems. Economic dispatch it is used, optimal power flow it is used, okay, expansion planning, almost all gradient method is more widely used like Newton's method. Let us see what is gradient method. The gradient method works on the principle that a minimum of a function can be found by a series of steps that moves away in the direction. Inward direction. This is the gradient of the function, okay, and it always points in the direction of minimum ascent. If we have to move in the direction of minimum descent, we should take the negative of this. X0 is the initial point. This is the gradient of function into alpha. Gradient of this function is the first derivative with respect to the variable. X nu is equal to x old minus gradient of the function into alpha. Okay. I can write like this. How do you formulate this objective function to be minimized? This is the equality constraint. The Lagrangian function is objective function plus lambda times equality constraint. Okay. If you take the gradient of this function, here f, instead of f, I take the complete Lagrangian. Okay. Okay. This is called gradient of the Lagrangian is dou L by dou P1, dou L by dou P2. This is partial derivative of dou F1 by dou P1 minus lambda. We have for with respect to P and this with respect to lambda. Because there are 3 units, we take partial derivative with respect to P and also with lambda. This is what is the gradient of Lagrangian function. Okay. Now variables are P1, P2, P3 and lambda. We have to equate this to 0. Once you equate this to 0, and we calculate the new value as old value minus gradient of this into x into alpha. Let us see how this works. Okay. The same problem I considered. Here instead of 850 megawatts, I assume a load of 800 megawatts. Take initial values of P. Here also you have to take initial value of P. And once you know the initial value of P, the step 2 is to determine the initial value of lambda. Okay, remember I said, how do you select the value of lambda? Okay, here the heuristic or rule of thumb is once you know the initial value of P, you take the initial value of lambda as average of the incremental fuel cost. Take the average of the incremental fuel cost of each. Okay, then you'll get 9.4. That means you started with P and you get the average value of lambda. Okay, then you try to solve. You see here, this gradient method has taken 10 iterations. Okay, but how do you know this is the best? The lambda keeps on changing. The cost keeps on increasing. Okay, at the 5th iteration, this method got the best solution. But at the 10th iteration, cost is more, okay, but lambda is different. So this method is, the drawback of the gradient method is that the initial values of P, even though it is converging, after some iterations, it may tend to diverge. So you need what is called a reduced gradient method. In this reduced gradient method, we assume that one of the generator is always a dependent variable. That means it can be removed from the formulation. You have P1 plus P2 plus P3 is equal to 850. I write P3 in terms of P1 and P2. Okay, so the cost is so the cost function only will be a function of P1 and P2. So the number of variables will be only P1, P2. Earlier it is P1, P2, P3 and lambda. If I remove P3 from this and write P3 as a function of P1, P2, I'll get only P1 and P2. The size of the dimension also is reduced. This is what is called the reduced method. If you compare the gradient method and reduced gradient method, okay, here dimensions are more, here dimension is less. Only 2, here there are 4. Okay, the gradient also is less. So reduced gradient method is, suppose you see the solution. Okay, original gradient method and reduced gradient method. In the reduced gradient method, okay, I started with alpha is equal to 10. I got the same solution. The P total remains the same. Okay, the result has converged. The cost is same. Whereas the same original gradient method, no, the cost has increased. Okay, lambda has diverged. Okay. Here, I try to fix the equality constraint as same. Then I try to calculate P1, P2, P3. P3 as a function of P1, P2. Even though it took more iterations, this is consistency of solution. So look at the observation. Original gradient method might diverge. Okay, reduced gradient method will always converge. Okay, and this is widely used in optimal power flow studies. This is the advantage of reduced gradient method. Reduced gradient method is most widely used for economic dispatch. It's an iterative method. It is bound to converge. Okay, it uses all the principles of Lagrangian method and lambda method. Okay, and reduces the number of variables used. Next, coming to Newton's method. This is the last method which we will discuss. Newton's method is an improvement over gradient method. Okay. It has better convergence characteristic. Let us assume a function g of x to be 0. If I perturb by delta x, g of x by delta x is 0, the solution of this can be written as g of x plus g dash x delta x. Okay, if I expand this by Taylor series, okay, I take g of x plus dou g by dou x into delta x is equal to 0. This is how the Newton's method works. From which I can write delta x is equal to by this relation. From this relation, I can write delta x is equal to minus g dash x inverse into g of x. This is how the Newton's method works. The Lagrangian objective function plus the equality constraint. We take the partial derivative of the gradient of L of x. This is how it comes. Okay. You see the example, same thing I have written here. A typical example, same problem if we use Newton's method. Okay. This is called the Hessian matrix. Okay. This is called the gradient of the Lagrangian. P1, P2, P3. Okay. I calculate H1. I can once you know this one, I can calculate P1, P2, P3 in one step. So in 2 iterations, you will get a solution. The Newton's method for economic dispatch is best method, but only problem is how do you consider losses in this? How do you consider inequality constraints? Till now, no one has done this. They say they solve Newton's method and assume that all values lie within limits. But what happens if one of the limit generation hits the limit? Okay, this is where the challenge lies. We assume if all units lie between the point, it's okay. So Newton method assumes that the initial starting point should lie within the limit. You should get an approximate solution to the initial starting point. If the initial solution is not properly chosen, the solution will diverge. Okay. We did try to simulate with another method. Okay. The typical example of Newton's method with B-loss coefficients. How to calculate the Hessian matrix. Here we have to assume the initial values. Okay. If you don't select the initial values, you'll not likely get a solution. Okay. Whereas the gradient method, you assume the values of P and try to calculate lambda and so on. But Newton's method is entirely different. You should know the exact value of the initial starting point. Any error in calculating the initial point will result in divergence. This is how it is done. Newton's method. I don't want to go in detail. It takes in 4 iterations, you will get a solution. Okay, but only thing you can't consider transmission losses in Newton's method. That is a drawback. There are several examples which I have considered. Different examples. I think time is almost over. Let me show some important things. There are various examples how to be solved with losses, without losses, transmission losses. Same. Okay. I showed in detail calculations without losses. And before stopping, I'll say what is unit commitment. Unit commitment is determining which unit to be used on and off. Okay, there are many generating units, thermal units, hydro units. Okay, selection of units. You can switch on or switch off units such that the total cost is minimum. Okay, this is the difference between unit commitment and economic dispatch. Same. We have power balance. We have constraints. Okay. Here in economic dispatch, you use quadratic programming and nonlinear programming. Whereas in unit commitment, you use mixed integer programming because the units can be on and off. Okay. Here we have spinning reserve. Okay. Generation capacity. Many other constraints come into unit commitment. Whereas economic dispatch, you have only power generation minimum limits. You can even include voltage limits, but minimum thing is minimum and maximum generation limits. Okay. So mixed integer nonlinear programming is the widely used method for unit commitment. And this is a very complicated method. Sometimes it may take hours to solve this. Because if you want to do for 15 number of units for 1 month, it takes several hours to solve. Dynamic programming is the best method which is widely used for unit commitment. So these are various objective functions, constraints, minimum uptime, ramp time constraints, uptime limits, ramping constraints. Many constraints are there. Another is a emission constraint. Unit commitment, usually coal-fired plants are there. You have to minimize the amount of emission generated. This is another called emission constraint unit commitment. Okay. We try to fix or cap the amount of emission which can generate, and then try to adjust the generation in such a way that total generation is more. This is where renewable energy is coming into picture. Okay, because of the coal-fired plant, we want to use renewable energy like wind and solar to take care of the thermal generating units. Next is called stochastic unit commitment. I said with renewable energy, because you need renewable energy to remove the coal-fired plants, So renewable energy is not deterministic, it is stochastic. Uncertainty is there. There's no uncertainty in generation. Okay. So variable fuel, all these things, uncertainties, if you consider intermittent renewable generation, this is called a stochastic unit. This is where probability comes into picture. Probability density functions, uncertainty. That's why because of this, various methods like fuzzy logic techniques are all used to handle uncertainty in problem solving. Next is called security constraint, as I said, unit commitment. Okay. Where you consider the line limits. Okay. Abrupt changes in the load, some of the units drop off. Okay. Suppose there's no natural gas, then how do you use another units to supply? This is what is called security constraint. I don't want to go into optimal power flow. This is an extension of economic dispatch. And the new terms in economic dispatch is called market-based economic dispatch. Okay, I'll complete in 2-3 minutes. This is a market-based economic dispatch which is gaining more importance. Okay. Here, the Central Electricity Authority in India, with privatization of generation and distribution, okay, distribution companies, okay, they have what is called as private generators coming into picture. Then you have the price is variable. Here we assume the price is fixed in ordinary economic dispatch. That is called cost-based economic dispatch. Market-based economic dispatch is called price-based economic dispatch. But price is a variable. Once price becomes a variable, then the challenge becomes more. More control variables come into picture. This is what is called market-based economic dispatch. Various discoms come, gencos come. You have to find a bidding price. You have to select the price of operation. Okay, that means the price is nothing but the lambda. Each companies try to compete to get the contract. So this is where game theory comes into picture. This is called strategic bidding. Economic dispatch leads to what is called as strategic bidding. Lot of this is where the Indian market generation companies, India Power Exchange. This is a very challenging topic in India Power Exchange. They want to know if different people participate. They compete with each other. Okay, the lambdas will be different. How do you know which is operating lambda for each unit? So lambda is what is called the bid price. So they'll auction the bid price. They'll auction the generation and the price. There's a confidentiality involved. Okay. This is done every 15 minutes. In a real-time energy market in India, we have PXIL, Power Exchange India Limited. Every 15 minutes, economic dispatch is done. The price keeps on changing. I didn't show this because it will take a lot of time, but price-based economic dispatch or market-based economic dispatch is presently being carried out by the Indian power companies, where private people come into picture with different values of lambda. Okay, they want to supply power at a cheaper price. Okay, so this is where the competition and cooperation of electricity comes into picture. This is what is called market-based economic dispatch. Okay, how competition, see, this is called competitive generators. They come to supply, okay, and meet the demand. This is what is called aggregators. I introduced energy markets, aggregators. Okay, competitive generation come into picture to supply the power and meet. Okay, this will reduce the total cost of operation and improve the reliability also. And final slide, conclusions. Okay. Parallel or interconnected operation of power systems improves both the reliability and economic operation. And power system optimization is an interesting and challenging topic, which is continuously evolving. Convex optimization is the most recent technique which is used for economic dispatch. Economic dispatch, unit commitment, and optimal power flow are three widely used, most commonly used methods in power system operation. And extension of economic dispatch are gaining importance. These are called the security constrained operation. security constraint economic dispatch, security constraint unit commitment, security constraint optimum cost. The recent trends are called market-based economic dispatch or price-based economic dispatch. These are the current trends which are happening now. Every 15 minutes, economic dispatch is done. This is what is called real-time economic dispatch. So economic dispatch is one of the programs which is widely used in a control center. Any questions? I've taken a lot of time.
Naidu sir.
Sir, thank you very much.
Sir, thank you. I've taken more time than required.
No, it's okay. Because at least these students got an idea about,
sure.
you started from the big, basics.
Yes,
And
yes.
then talked about unit commitment, and you have given an idea about market-based economic dispatch,
Yes, sir.
which is the recent trend actually.
True, sir.
And this power exchange economic dispatch is the need of the hour. So I'm really, I humbly thank you for your lucid, talk on this important, important area of power system, which ultimately gives you economy, savings also.
Yes,
And this has to go a long way. So I thank you from the bottom of my heart that you have accepted my invitation, sir.
yes,
And I thank on behalf of GHRCE College of Engineering that you have really enlightened us about the recent scenario about economic dispatch. Thank you very much for your valuable contribution, sir.
Okay, thank you very much.
We want to associate with you in future also.
Sure, sir.
So on behalf of our director, chairman, and every senior member in electrical department, I thank you once again, sir.
Yes, sir.
Thank you very much.
Welcome, sir.
Thank you very much.
Thank you.
Thank you, sir.
Thank you.
Thank you. Thank you.
Swarup sir, you can switch on your video.
Yeah, 1 minute, sir. I'm trying to see where it is. I'm not able to see.
Kindly, yes, sir.
Start video.
Now I'm coming. Sir. Yeah.
ऊपर नहीं जा रहे ऊपर ले लो सर ग्रीन में ले लो ना
हाँ ग्रिड में
ग्रीन में
ग्रिड में
आ रहा है क्या
हाँ हाँ एक मिनट सर Okay, sir.
Okay. Okay, thank you, sir. It has taken more time, but I hope the students have benefited.
No, thank you, sir. Thank you very much.
Okay.
Thank
you.
Thanks a lot. Thank you very much.
कितना काम करोगे तुम?
Thank you very much.
Okay.
जीटी है ना
नहीं ग्रीटिंग में नहीं आई किसी को तो आती नहीं थी इसलिए नहीं
लिया ही नहीं गया
नहीं क्योंकि वो गुस्सा पे लिए जब तक
लिया गया क्या था मालूम
इसमें कैमरा दिख रहा था ग्रीड में बस आपकी एक को था इसमें और नहीं इसलिए
प्रिंसिंग इतना आ रहा है सर कुछ
हाँ
प्रिंसिंग इतना